In this third video for Module 16, we consider floodplain features and deltas. Well, we've talked a little bit about lateral erosion, and here we're going to take a look at some floodplain features, and these are things associated with meandering rivers. One of those is where a river decides to take a shortcut. You can sort of see where I've drawn that on here in the solid red line. This is called a cutoff meander, and they're pretty common in floodplains associated with big rivers like the Mississippi River. Here's a cutoff meander you can see right here near the center of this video where an Oxbow Lake has been created, and that's actually one of the next features we're going to look at here, Oxbow Lake. This is time-lapse photography over a series of years. So Oxbow Lakes represent where rivers flowed at one time, and a cutoff meander left them behind. In order to sustain themselves as lakes, they have to have sufficient water flow over time. If they don't have that sufficient water flow, they become oxbow swamps, and we'll look at those in just a second. Here's sort of the process that produces an Oxbow Lake through this series of little mini slides here. So we have our fast flow that I'm showing here as the cutoff meander continues to, or I should say the fastest erosion here on the outside bank continues to push towards the other part of this bend. Eventually you'll have a cutoff meander, there's the cutoff meander, and then potentially an Oxbow Lake. Where there's not really sufficient water flowing into an Oxbow Lake, over time it can become an oxbow swamp. So it's simply just a boggy environment with less water flowing in and less water flowing out. So oxbow swamps dominated by trees with a little bit less water. And then we see a number of places that may have been oxbow lakes or oxbow swamps at one time that are now just simply described as meander scars. They represent former channels of the river. And if you fly across the U.S., and in particular if you fly over a big river like the Mississippi, you'll see these everywhere along the river. Natural levees are places where the river will push sediments off to the side and out of the way. And natural levees, I mean, they're a little bit like man-made levees, except they occur in a completely natural way. But just where sediment is pushed out of the way, and it produces a little bit of a rise on either side of a river like the Mississippi. And finally, outside, sort of beyond the natural levees, sometimes you have swamps that'll form. We call these back swamps, and they're just, as I say, they're on the other side of the natural levee. And on either side or even just one side of a river, so back swamps. Let's talk a little bit about valley lengthening, and this is looking at how rivers get longer. And we're going to talk about two ways that rivers get longer. Valley lengthening is one, the other is delta formation. So the principal way that valleys get longer, headward erosion happens closest to those first order streams. So this is where gullies just sort of morph eventually into first order streams being those that have no tributary. They're very small, just trickles of water. So headward erosion is where these gullies are pushed farther and farther up valley. As I mentioned, the other way that rivers get longer is through delta formation. So that's at the other end of the river as it flows into a lake or a big body of water like an ocean. We'll look at that in a little more detail here in a few minutes. So we'll start with headward erosion. Again, these rivers and streams that have no tributaries flowing into them, these are first order streams. First order streams will push up into higher elevations. We sort of see that example here. I've added this dotted line here so you can sort of imagine, how these gullies might continue to sort of reach up like fingers reaching up into higher elevations. So as you watch my animation here of these blue lines sort of growing and getting longer, that's how headward erosion works. And headward erosion can also produce some sort of interesting thing with streams. So here in this example on the left, this is a sort of a map view of two streams. You have stream A and stream B. What's going to happen here, I'm going to animate this, and stream A is going to continue moving to the right, and what it's going to do, it's going to capture the water coming from stream B and redirect that water. We call this process stream capture or stream piracy. So here's the capture stream as it moves towards stream B. It hooks up with it, connects with it, diverts water from it, and we have stream A as the capture stream, and stream B as the beheaded stream. So that's the term that's used to describe a stream that's been cut off, a beheaded stream. And here we see the same idea here in these two graphics on the right. So I mentioned that delta formation is the other way that rivers get longer. Imagine that rivers are carrying sediment, and the water is moving in a river fairly fast, and when it flows into a body of water like a lake or perhaps the ocean, the velocity of the water goes from whatever it is flowing in the river to near zero. And the ability of the river to carry sediments in suspended load, or bed load for that matter, also goes to zero. So what happens over time is sediments begin to pile up, just sort of pile one layer on top of another layer. And what the river does is it tries to find a way around. So it sort of pushes the sediments out of the way. Sometimes it breaks off into multiple channels. We call those channels where the river divides itself, we call those distributaries. And here in the photo on the left, you can see a number of distributaries here associated with this delta. On the image to the right, you can see, sort of imagine how these sediments are sort of piling up and sort of getting in the way and causing the river to form these distributaries as it pushes off in different directions. Let's take a look at some types of deltas for a moment. In some areas, like the Nile River in Egypt, we have what are called wave-dominated deltas. So these deltas tend to be reworked by waves, in this case waves in the Mediterranean. So the sediments continue to be carried by the Nile River, but they pile up, they get pushed out of the way by distributaries, and then they get reworked by waves. Another type of river delta is characteristic of the Mississippi River as it enters the Gulf of Mexico, and this is a river-dominated delta. This is where the sediments create new land. Of course, a delta is where new land is created, but the sediments form like fingers pushing off in many different directions. So if you see a river delta, it looks like a lot of little fingers sort of pushing out in several directions. You're most likely viewing a river-dominated delta. And then finally, we have some deltas that are dominated by tides. As tides go up and down, the tides are what rework the sediments, and that's what's happening here in the Bear River, California. Tide-dominated delta, where the sediments tend to be rearranged somewhat by the tides, ocean tides going up and down. And we'll take a quick look at a couple of these, some examples. Here's that wave-dominated example I gave you, the Nile River, one of the few rivers that flows north, flowing from Central Africa into the Mediterranean Sea, and there's the delta in that green, and you can see the sort of view. If you were standing there looking at it, you wouldn't necessarily know what type of delta it was, but this is in the area of the Nile River Delta. So again, a wave-dominated delta, and another view from the ground level, if you will. And then here's a view of a river-dominated delta in the Mississippi River Delta, the example I gave before, and you can see those fingers of the distributaries as they push off in every direction. So you can imagine sort of these channels sort of breaking off, pushing sediment, sort of trying to get it, pushing that sediment out of the way, maybe breaking off, going a different direction, and you have additional fingers that form of these of the delta sediments. So each one of these separate channels that breaks off from the main channel, a distributary. And here's what it looks like again from a sort of a ground level view of the Mississippi River Delta. One thing about the Mississippi River that's sort of interesting is that it takes quite a journey out into the Gulf of Mexico to find water that it doesn't have a lot of sediment in it, because there's just so much sediment that's carried by the Mississippi River Delta, or Mississippi River in the Delta. So this is sort of a dividing line here. You can see the very turbid water with lots of sediment still being carried on the left-hand side, and on the right-hand side you see the clear water of the Gulf of Mexico. So one question I have for you to think about: why has the sediment load of the Mississippi actually decreased since about 1700, since Europeans started arriving, I suppose, in North America, in the United States? So in this diagram we're showing in the blue, we're looking at the sediment that's carried by the Mississippi River and its tributaries, and the sediment contributed by its tributaries. So we have the Ohio River flowing in, we got the Missouri River carrying quite a bit of that sediment. The wider the line, the more sediment's being carried. So basically the Arkansas River carrying some, Red River that forms the boundary between Oklahoma and Texas carrying some, and all of this is flowing into the Mississippi River, which ultimately flows into the Gulf of Mexico. So we have a whole lot of sediment being carried in 1700, but look at the sediment that's being carried today. And I just put some representative cities on there as well, so you could see the location of St. Louis, Missouri, and Vicksburg, Mississippi. So it looks like the Red River, it's a little bit less. Arkansas River less, Missouri River less, Ohio River a little bit more. But you can see that the sediment load that's carried by the Mississippi River in more recent years is much less than it once was. So why would that be? So pause this video for a second, sort of give that some thought, and then restart the video. Well, if you came up with trying to, and this is a look here at the way the river might have looked around 1790. So the Mississippi River, this is not the Mississippi, but just a similar river to it, but here it's filled with carrying lots and lots of suspended load. And this is what the Mississippi looks like. This is a real picture of the Mississippi in the lower photo. It's what it looks like today. It's much clearer, not nearly as much turbidity and material. So did you come up with a theory about why the Mississippi River is carrying less sediment today? Maybe you said this. Maybe it has something to do with dams on the Mississippi River's tributaries. There are also a number of locks that are used for moving ships up and down the river. But dams and locks do have an effect on the sediment load because they hold back sediment. They trap sediment. So if you came up with that thought or that theory, you were exactly right. Let's move on and talk just briefly about a tide-dominated delta. Here we have the Tigris and Euphrates rivers in Kuwait. This would be a tide-dominated delta. So we have big lobes of sediment that have built up there. I kind of circled that location here, and just Saudi Arabia and Egypt shown on this map in yellow just for reference. But this is a tide-dominated delta. And the view on the ground in the Tigris River delta, so you can see what it looks like, lots of vegetation. Really isn't, it's really hard to tell what type of delta you're looking at here from the ground level. Another tide-dominated delta is the Ganges River, Bangladesh and India. So again, it's reworked by rising and by tides that go up and down. And the sort of the look from the ground level, the Ganges River with rice being grown. And then finally, we have another tide-dominated delta, one more, the Mekong River Delta in Vietnam. So Mekong River made famous during the Vietnam War, lots of fighting along the Mekong in southern Vietnam, and a view of the Mekong River from the ground level. We threw on one more here. This happens to be the longest river in the world that doesn't have any type of impoundment, any type of dam, and it's the Fly River in New Guinea. And I just thought I'd throw that on as well. So longest river without a dam, 650 miles, but the tide-dominated river there. So when you look at this river in the animation, this is the Po River Delta in Italy. This is an animation that kind of starts in 1604 and takes you through about 1985. What type of delta is this? From that list that we looked at a little bit earlier. If you said river-dominated delta, you're exactly right. So those fingers, those lobes, those distributaries are sort of pushing off in every direction. Exactly what you find associated with the Mississippi River. That's what we're talking about. Okay, there are a few rivers that are affected by both waves and tides. The Niger River in West Africa is affected by both waves and tides, so it has sort of an unusual coastline. And finally, I wanted to end by bringing up one river that doesn't have a delta, the Amazon River. So that seems really strange. The Amazon is as big as the next several rivers put together in terms of the discharge. It's massive, and yet it has no river delta. Why? How could that be? Well, it has to do with the fact that the sediments that are carried by the Amazon have a pretty steep drop-off, and the waves from the Atlantic Ocean tend to sort of spread those sediments out over a very large area. So it doesn't, the waves and the wave and current action really has not allowed a delta to form there at this end of the Amazon River as the Amazon enters the Atlantic Ocean. Here's what the presumable where we expect to see a delta, and you really see no delta here.